Okay, in this part of my lecture, I'm going to discuss the design requirements, or how to specify requirements for the design, which is an important aspect of control design because you need to know what is expected and what you need to achieve with your design. So you really need to know the aims or objectives for the design as my first step. In general, when you design a closed-loop system, you want to achieve stability. So if the system is stable, you don't want to make it any worse. If the system is unstable, then you have to find a way to stabilize the system. And on top of that, you want to achieve a good performance. And I will talk about that later. But you also want to achieve certain level of robustness. That is to say that if you design a control system, you assume you know the system, i.e., for example, you know the transfer functions of a system. But often in real life, a plant can change over time. The performance can degrade. The parameters may vary a little bit, but your controller is what you designed. So the controller has to take into account that kind of change. It's called uncertainty because you don't know what's going to happen in the future, how the plant might change its behavior. But your controller, the controller you design, must be still working when the plant changes a little bit. That's the issue of robustness. But we're going to focus on the performance requirements. In general, we want smaller steady-state error. If we can remove the steady-state error, that's even better. We want fast response, fast transient. It takes less time to get to what you want to achieve. We want less overshoot. We don't want overshoot to be too big. We want smaller settling time. But also we want system to work well when there are disturbances. So we want a good rejection of disturbances. On top of all that, we don't want very expensive system. Therefore, your control signal or the power requirement needs to be low. So you don't want to over-design your system. That's our starting point. So if I start by just give you a reminder of the definitions of key parameters for performance measurements. There's rise time. That's the time it takes for the system to respond from 0 to 90% of the final value. We want less overshoot. The overshoot is defined by what is the part that goes above the final value divided by the final value, okay, in terms of a percentage. So it's that bit divided by the final value there. We want less settling time. That is the time for the response to reach within 2% of the final value. That is indicated as TS here. But also we want steady state error to be under control. That's the difference between the system desired output and the real output. So that's steady state error. All four parameters are fairly typical when we design feedback control systems. To study the relationship between these parameters and the parameters of a system in the transfer function, like quarter frequency, like damping ratio, like natural frequency, like DC gain, that kind of stuff, we need to examine how a typical system behaves with different parameters. For example, a first-order system, we will have a transfer function like either this, okay, in the first standard format, or like that in the second standard format. where tau is my time constant, omega naught is my corner frequency. Now you can see here we have a pole of minus omega naught, because if I equate the denominator terms to 0, I get SP equal to minus omega naught. For the second order system, the standard format is like that. And we have the natural frequency and the damping ratio to consider. Now I have not included the DC gain in either first or second order transfer functions, because it is something I will discuss later in the second part of this lecture. Now for the second order system, we can also find the poles. Now typically if it's underdamped, we have equation number 5, because that gives us the real part. Imaginary part is easier to discuss, and it represents the real second order systems. If you have two real poles, then you can consider them as first order or two first order systems connected together. So I'm going to look at how the corner frequency or natural frequency affects the performance and how the damping affects the performance. Now for a first order system, if I just tune the omega naught to use different values, say 1, 2, 5. Now, when the corner frequency equals to 1, this is the red line is what we get. Okay, so it goes up and then settles down to the final value. If I increase the value to 2, and we get the blue response. If I get the corner frequency of 5, we get this green line in its response. So typically, therefore, the higher the corner frequency, the fast response we get. So the response is related to the corner frequency, or for the second order system, it relates to the natural frequency of a system. So the frequency matters. Frequency indicates a response time. Now, if I fix the frequency and just look at the damping ratio in a response, what you see here is that when the damping is high, I get this kind of response. It's slower, but there's no overshoot. If I increase that if I reduce the damping ratio from 2 to 1 to 0.7 to 0.5 to 0.2, then you get 2, 1, 0.7, 0.5, 0.2. So you can see the response goes up, but overshoot also increases. So to summarize, the natural frequency or corner frequency tends to make the system response faster, but the damping ratio, if we have a lower damping, it tends to increase the overshoot. So based on this kind of analysis, the control engineers in the past actually have come up with a set of empirical relationships between the rise times, overshoot, settling time, that kind of stuff, and the corner frequency, the natural frequency, or the damping ratio. These are given like this. If we want the rise time to be less than a certain value, then the natural frequency of your system must be greater than 1.8 divided by the rise time. If we want certain overshoot, OS here stands for overshoot. Okay, if we want overshoot to be less than this value, then the second formula, the equation number 2, defines the minimum damping you need of a system. So it's 0.6 times 1 minus the overshoot. If we want the settling time, TO here represents the settling time. Then we want the real part of your complex poles on the left-hand side of this value, 4.61 divided by the settling time. So because they are both negative, therefore, if I reverse that relationship, if you multiply -1 to both sides, then the real part, or the absolute value of the real part, must be greater than 4.61 divided by T naught. That's just a simple math relationship because this is what we want to do. Now that's kind of calculations you first need to perform. So say directly from rise time, you can calculate minimum omega n. From overshoot, you can work out the minimum damping you need. From settling time requirement, you can work out the minimum damping times omega natural frequency we want. But often we also need to represent this in a graphical manner, in a complex plan, or in the S-plan, if we like. So we need to actually do a little bit more processing than this. Now in equation 1, this equation gives me the poles of second order system. The real part is minus zeta omega n. The imaginary part is omega n times square root 1 minus zeta square. That cause when you solve the characteristic equation, give you the poles for the second order system, this will be a complex number. It's a complex number in the rectangular form. But of course, we can convert that into the polar form as well. Okay? So this is what I do. First of all, I'm going to look at the real part because that's one of the requirements in the DesignSpec. If I just go back there, that's the real part, minus zeta omega n. So I'm going to look at this. I know if I have poles, I know the real part is minus zeta omega n. Then I'm going to find m from that solution. M equals to square root of this square plus that square. There's a square root missing, overall square root. Okay, there's a square root this and a square root of that. If you add this to this together, now put square to here, put square to that, that get rid of the square root. This becomes omega n square times 1, omega n square minus zeta square. Okay, omega n square times zeta square cancels zeta square omega n square out, and therefore I end up omega n square and the square root. Remember, there's a square root missing, there's a square root missing here. So I end up with omega n. That means the magnitude of the poles is actually equal to the natural frequency, omega n. Okay, so magnitude is not related to damping. Damping cancels it out. Okay, the damping cancels that out, and the magnitude of the pole is actually omega n. So now I have equation 2 and equation 5. Just remember that. Now I'm trying to work out the phase angle, this theta. Well, I actually use a different angle here. I use phi. So you say, imagine that's phi. Okay. If I look at the complex number of this is my pole pointing towards that cross. Okay, that's my complex number. The real part is minus zeta omega n. That's minus zeta omega n. The imaginary part is omega n times square root 1 minus zeta square. That's that part. Now this length, remember we work out from previous slides, this length, the magnitude, i.e. the m, equals to omega n. So this length is omega n. It's the same as the natural frequency. So m equals to omega n. That's defined in the equation number 5. Now, if I look at that triangle here, this right angle triangle. This side divided by the magnitude. This side is phi omega n. Magnitude is omega n. So phi omega n divided by omega n equals to, zeta omega n divided by omega n equals to zeta. That's my cosine angle. So cosine phi equals to zeta. So this angle is directly determined by the value of zeta, the damping ratio. In other words, if we want certain level of zeta, then we can work out the angle we want. Because the cosine, so it's an inverse relationship. Cosine for the first from 0 to 90 degrees, as the angle goes up, cosine goes down. So this is the maximum angle we can allow. So for a minimum damping value, this is the maximum angle we allow. So you use phi cosine, arctangent cosine for zeta, that gives us. So we have 3 relationships. One is the real part of the poles. The other one, the second one, is the magnitude equals to omega n. The third one is the maximum angle phi, that's cosine, arc cosine damping ratio. And therefore, for a set of requirements, say we want certain level of omega n because the rise time, we want certain level of damping because the overshoot, we want certain level of the settling time, that's the real part. We can form this. For certain level of rise time, that will give us the minimum omega n, which is the magnitude of the poles. Magnitude is the length between any point to the point of origin. So that's the length there. So therefore, if we have poles outside of that half circle, the radius of the half circle is omega n, that's the natural frequency. Then we will meet the rise time requirement. Okay, so from rise time, you work out omega n, then you draw a circle here. We want all the poles to be outside of that circle. To have the overshoot requirement, we want the maximum phase angle, which is defined by arc cosine zeta. So we find that angle, we draw 2 lines. One is that line, the other one is this line. So this is the angle phi, this is the angle phi as well. Okay, so for the damping requirement or for the overshoot requirement, we can work out the minimum damping required. Therefore, maximum angle we can allow. So we want the poles to be inside of these straight lines. Okay, if poles are inside of the straight lines, then they will meet your overshoot requirement, or they should meet your overshoot requirement. For the rise time, we want the values, the real part of the poles to be on the left-hand side of minus zeta omega n. That's your minimum requirement for zeta and times minimum requirement omega n. And this, because the real part, this green line indicates the real part, because the real part of any point on here is the same. But we want the poles to be on the left-hand side of that green line. So rise time, it's that half circle. Okay, we want them to be outside of that circle. Overshoot requirement is that angle here, and this angle there. We want poles to be inside of these 2 straight lines. The settling time is this green line. We want the poles to be on the left-hand side of that green line. Okay. Now, for a system to meet all 3 requirements, you have to have your poles in the area that's shared by all three requirements. Okay, so it's this red dotted line that I indicated here. You need poles to be on the left-hand side of this line there. Because if you have a pole there, you can meet the, it is outside the half circle, therefore it meets the rise time. It is inside of these two straight lines, so therefore it meets the damping requirement or overshoot requirement, but it is only right-hand side of the green line, so it's less likely to meet the settling time. Same argument for here. Okay, if we force into this region, it's okay for the damping requirement because it's inside of these two lines. It's okay for the green line because it's on the left-hand side, but it is inside of half circle. So this area is less likely to meet the rise time requirement. So all three, just to emphasize again, to meet all three requirements, it needs to be in the area shared by all three lines. Okay? That's how you interpret the requirements of rise time, overshoot, and settling time in a graph or in the S-plane. So how to find the regions in the S-plane where you want the poles to be. Now remember, if we want a system, in the early discussions, we said if we want a system to be stable, we want the poles to be on the negative side of the S-plane, i.e. on the left-hand side of the imaginary axis. But to meet these requirements, you need to go further. You need to push the poles further towards the left-hand side. This actually helps you to define where we should put poles. Then we have the last requirement to discuss, which is the steady state error. To discuss a steady state error requirement, we need to take a different approach. Now over here, I have a simple closed-loop system. I have a K here, I have G here. The transfer function between R, the input, and Y, the output, will be G times K over 1 plus G times K. That's the transfer function. The transfer function between the input and the control error will be, because there's no terms between, so the numerator will be 1, the denominator terms will be the same, so it's 1 plus G times H. That's the transfer function between R and E. Now to make it clear, if we want zero steady state error, we want a DC gain of the first transfer function to be 1. But we also want the DC gain of the second transfer function to be 0, because that's the error output. Okay, that's this first requirement. First transfer function says the relationship between input and output, so we want them the same. That's what, therefore, we want DC gain to be 1. But for the second transfer function, we want control error to be 0. So whatever input you have, I want this in steady state to be 0. So the transfer function, the DC gain here, for this transfer function should be 0. Now previously, we also discussed the PID control, and we showed that when you have a pure integrator, if you add an integral gain to the system, to your controller, it has the effect of eliminate the steady state error. Now, integral, the transfer function of integral term is 1 over S. 1 over S, think about that. The pole, without anything else, without closed loop, just the controller itself, the pole 1 over S equals to, will give you a pole of S equal to 0. So that's the effect of the integral gain. When you don't have integral gain, then you don't have that 1 over s. Therefore, the steady state error will not be 0. Now, the idea of integral gain only works to a certain extent. And sometimes you don't need it. If there's an integral part in the GS itself, it would act as the integral. In this case, it would also work to remove the steady state error under certain conditions, which I will discuss a bit further later on. Let's assume we have no, for the time being, let's assume we have no 1 over s in the controller, i.e. no integral gain. We have no 1 over s in the GS, that's a plant. A system like that, when you close the loop, we call a system like that as a type 0 system, because there is no pole at s equal to 0. i.e. GS, the DC gain of GS is not infinite. The DC gain of the KS is not infinite, because there is no 1 over s. If there is 1 over s, you make s equal to 0, then the gain will be infinite. 1 over 0 is infinite. So let's assume we don't have that. We're going to apply the final value theorem, the one that I introduced during the discussion on Laplace transforms. I'm going to use this transfer function, the second transfer function, to discuss the steady state error, and I want the DC gain to be as small as possible. If 0 would be even better, because 0 would give me a 0 steady state error. So I'm going to apply that and apply the final value theorem. Final value theorem says my final value of the control error ESS, SS stands for steady state, or the control error value when time tends to infinite. When time tends to infinite, the final value theorem says we need to multiply the transfer function by s, and then we need to multiply that by input as well. Now let's assume we have a unit step input. The Laplace transform a unit step input is 1 over s. So I'm going to multiply 1 over s here. This s cancels that s out. When the limit tends to 0, this is a DC G0 will give me a DC gain of the plant. K0 will give me a DC gain of the controller, which is K times P bracket 0. That means that if I multiply the two DC gains together, that will give me the DC gain of Kp. So the steady state error in a type 0 system, that is the open loop with no poles at s equal to 0. If the input is a unit step, then we can work out the steady state control error by finding the DC gain of G, that's a plant, find the DC gain of the K, multiply the two together, that gives me a Kp. 1 over 1 plus Kp, that is a steady state error. So obviously, if we want to reduce the steady state error, I need to somehow increase that value. Either increase the DC gain of K, or if your plant has a higher gain as well, that would help. Okay? That only works for the unit step input. If the input is a ramp, now unit ramp, for a unit ramp, the Laplace transform of that is 1 over s. So if I apply the final value theorem for the Laplace transform, then I have that relationship. The final value or the steady state value of the error will equal to s, that's part of the final value theory times the transfer function times the Laplace transform of the input. That will give me 1 over s squared. This is 1 over 1 plus g times k. Now, s squared, 1 over the s cancels that s out, and I still have 1s left. This gs, we said earlier, because there is no pole at 0, so this gs, the DC gain of gs is a finite value. The controller doesn't have an integral gain, so that also gives me a finite value for the DC gain. So this term there will be a finite value. The second term here, this term here, because 1s is cancelled, but I still have another s here. 1 over s, when s tends to 0, 1 over 0, that gives me infinite. So I'll have an infinite control error. That when it settles down, or it doesn't settle down because this error just keeps going up. Okay, so for type 0 system with no pole at s equal to 0 for either the plant or the controller, the steady state error for the unit step input can be calculated with equation number 1. Kp equals to the DC gain of the plant times the DC gain of the controller. But the error would be infinite. The steady state error will be infinite if the input is the unit ramp input. So there's a limit what we can do with this type of system. That's why often we want to include an integral gain. Because now, if you think about it, 1 over s is the integral gain, then we will have a s equal to 0 for its pole. When you have a 1 pole at s equal to 0 in open loop, we call a system like that as a type 1 system. It may come, that 1 over s may come from the controller, it may come from the plant itself, but it doesn't matter. Once you have s equal to 0 as one of the poles, either in G, in open loop, or in K, then we have a type 1 system. Type 1 system is G in the G times K. Now, we know we have a 1 over s, so I'm going to take that 1 over s out of G times K. Let's assume the remaining part of G times K is GK1s. That's my transfer function without that. So the reason I'm doing it is making the life a little bit easier for processing. So substitute this into here, okay? I'll get the transfer function for the closed loop to be s over s plus gk1s. Apply the final value property of the Laplace transform. The steady state error equals to s times the transfer function times 1 over s if the input is unit step. Laplace transform of a unit step is 1 over s. So this s cancel that s out. I still have s left on the top. When s tends to 0, this becomes 0. This is not 0 because I've already taken everything out. Okay, so I have 0 divided by something, a 0 plus a value. Therefore, I get 0 steady state output. And so for type 1 system, if the input is a unit step, then the steady state error is guaranteed to be 0. Either because you have integral gain or you have a gain in the plant itself. But things change when I have a unit ramp input. Unit ramp input, so I'm going to copy this down, this equation down, except I'm going to change the input from 1 over s for the unit step to the 1 over s squared for the unit ramp. Now, s cancel that s squared out. Okay, so that s disappears, that S disappears. Then when S tends to 0, this disappears. The only thing I got left is the DC gain of GK1. GK1 is the open loop transfer function K times G times K, taking away one of the LS. So that will be giving me a finite value. So for type 1 system, if the unit ramp input is applied, then we have a finite steady-state error. The value can be calculated by 1 over kV. kV is the DC gain of the open loop G times K without 1 over S. I can go a bit further for type 2 system. That is where if I include a 1 over S square in the transfer function of the G times K. And you can go from there. If for the unit step, this is the transfer function of the closed loop from input to the control error. This is part of the finite value theorem. This is the Laplace transform input of a step. So this S cancels that S out. I have S squared there. When S equals to 0, this equals to 0. This is 0, but this is not 0. So 0 divided by non-zero, that equals to 0. For the ramp input, this is a transfer function for the control error. This is part of the finite value theorem. This is the 1 over S squared, that's the Laplace transform of unit ramp. S squared cancels that S squared out. This is non-zero. So when S equals to 0, this equals to 0. So it's 0 times a non-zero, that equals 0. So if we want 0 steady-state error for a unit ramp input, that means the output will follow the input exactly in steady state. Then we want a type 2 system where the open loop transfer function G times K will have 2 poles at S equal to 0. I can go on like that. Okay, so that is a summary of what we need to have. Okay, so this is the input, step, ramp. This is actually a t-square input type. This is like an acceleration type of input. Type 0, for the step input, the steady-state error is finite. The value can be calculated by 1 over 1 plus Kp. The Kp is calculated at the bottom in this equation. But type 0 doesn't work with ramp input, then we work with t-square. For the type 1 system, the steady-state error for the unit step input is 0. For the ramp input, the steady-state error is finite. The value can be calculated by 1 over kV. For the t-squared type of input, it doesn't work. Type 2, it works with step, with a 0 steady-state error. It works with a ramp, with a 0 steady-state error. It also works with t-squared, but with a finite steady-state error. That's 1 over Ka. Kp, Kv, Ka are all dependent on the open loop transfer function G times K. Okay, now the S here or S squared there just are there to try to cancel the S equal to 0 or 1 over S squared in the transfer function. Okay. So I'm going to do an example here to see how we can relate the requirements and translate that graphically onto the S-plan, and also what it means for the control error, that kind of stuff. Okay, so what I have here is an example of a satellite tracking radar. The GS represents the dynamics of that radar. The controller is K, and I have a feedback control here. Okay, the transfer function of the GS is 1 over S times 10S plus 1. What we want is as the satellite move across the sky from one side to another, we want the radar to follow the path. So we want the angle of the radar to follow that pattern. T is the time, so as the angle will increase proportional to time at the rate of 0.01. T is a unit ramp, but the input for this application is not a unit because it has a coefficient of 0.01. It's much smaller. What we want to achieve for the controller, there are 4 requirements. We want a tracking error or asymptotic tracking error must be less than 0.01 radians. That means the steady state error. For this input, 0.01 t, we want a step response overshoot less than 16% or 0.16. We want the rise time to a step input less than 6 seconds. We also want the settling time to within 1% of steady state error should be less than 20 seconds, okay, or 2%. So for the first requirement, the steady state error, now remember the input is 0.01 t. We want the steady state error less than 0.01. This is the same as to say that we want the steady state error to be 1 if the input is t, not 0.1 t. We multiply everything by 100. Okay? That will give us the unit ramp input, and for this we want the steady state error to be less than 1. Now first of all, we need to check what type of system we have. I have a K, I have a G. Now leave the K aside, just look at the G here. G has 2 poles. One is at s equal to 0. The other one is s equals to minus 1/10. So this s equal to 0 gives us a type 1 system. So I don't necessarily have to have an integral gain in the K because I already have an S. And we know a type 1 system will give us a finite steady state error to the ramp input. So I'm going to apply the Laplace transform, I'm going to apply the final value theorem to that. And bear in mind, this is what we wanted, the KV. It's a type 1 system. We want to work out the KV. So I'm going to do S times K times G, and then take a limit to S. That S, cancel that S out. And this S equal to 0, therefore this term becomes 0, so this part becomes 1/1. Therefore, that leaves us with a K. Now K is the transfer function of the controller. S tends to 0, that gives us the DC gain of the controller. The steady state error, control error, in this case is 1/kV. So therefore, if we want steady state error to be less than 1, then kV, or the DC gain of the controller, must be greater than 1. So that's our first requirement. We want the DC gain of the controller to be greater than 1. That's the first requirement. Second requirement, I want overshoot less than 16%. Okay, so I'm going to use one of the empirical formulas that we had before. So zeta, for an overshoot less than 16%, we must have a zeta greater than 0.6 times 1 minus overshoot. 60% is 0.16. So 1 minus 0.16 times 0.6, that gives us 0.5. Minimum damping requirement is 0.5. But we can actually work out the phase angle graphically for the poles. The maximum angle for the poles must be arctangent zeta. That will give me the degree 60 degrees. So the angle of the poles must be less than 60 degrees. Rise time is easy. It must be greater than 1.8 divided by the rise time. So omega n, the natural frequency, must be greater than 1.x divided by 6. That's 0.3. The fourth requirement is the real part, because we want settling time less than 20%. So the real part, we apply that the last empirical formula, minus zeta omega n must be less than minus 4.61 divided by the settling time. That gives me minus 0.23. So from second requirement, we got the maximum phase angle. From the third requirement, we got the minimum natural frequency. From the fourth requirement, we have the minimum real part of the poles. Now I can draw the region or the lines in the S-plane or the complex plane. Omega n, minimum omega n is 0.3, so I can draw a half circle with a radius of 0.3. That's omega n requirement. Maximum phase angle is 60 degrees. I'm going to draw a straight line here. I'm going to draw a straight line here. That's 60 degrees. That's 60 degrees. The real part is minus 0.23. I'm going to draw a vertical line at minus 0.23 here. That green line. So I have blue line for omega n, half circle. I have this sort of this part of what's that, purple or whatever, purple lines for the angles, 60 and 6. I have green line for the real part, and then I can identify the region that's shared by all three. So for that requirement, for that control requirement, for that control system, we need the poles to be on the area that's shared by all three regions. That's the one indicated in the red dotted line. Okay. So something for you to practice. You can actually follow my example to work out the regions. For this requirement, I have a rise time of 2 seconds. I have settling time of 15 seconds. I have overshoot of 20%. Work out the omega n, work out the phase angle, work out the real part, and then draw the lines and find the common region for that requirement. But you can also work out the rise time or estimate the rise time, overshoot, and settling time from the poles as well. Okay, because from the poles, we can work out the damping. We can work out the omega n, and then we just calculate this in the opposite way. Yes, let me just go back a few slides. Use the empirical formula. If you work out from omega n from the poles, then you can work out rise time, the likely rise time. If you know the damping from the poles, you can work out the overshoot. If you know the real part, then you can work out the rise time. The poles are given here. So you just work out all the way around for that second part of the practice question. Okay. Thank you.